So in this section, we're going to be taking a look at a very useful skill that is done all the time, which is estimating values with graphs. And the estimation can be done in a very formal way where you actually come up with an equation based on the data, or it can be done in a less formal way where you're really just eyeballing it. You're looking at the graph purely visually. And there are two important words that we need to understand: interpolation and extrapolation. So let's take a very simplified example. This graph at the top, we have collected two data points, and I haven't indicated anything about what these are or what we're measuring or what the x-axis or the y-axis represents. But let's just say we have these 2 points, and let's say that we make an assumption that there's a relationship here, and furthermore that it's a linear relationship, which would mean that there's a line passing through those 2 points. And that's not a very good line, but close enough. Some sort of line passing through those 2 points. And if we wanted to use this graph, let's make sure we know where the 2 points are. If we wanted to use this graph to make some predictions, if we are trying to predict some sort of value that's in between the 2 points, sort of in known territory, if you like, that is known as interpolation. If we're trying to go beyond the data, so if we're going to go way out here, that's known as extrapolation. And equally, the area to the left might also be known as extrapolation. Now, interpolation usually yields half-decent results if there's any relationship whatsoever. Extrapolation can be quite dangerous. So even if we can establish a linear relationship, which is not always the case, interpolation is going to yield a very nice result, but the linear relationship might break down at a certain point. And in other words, if we try to go beyond the data, we may be coming up with a prediction that just is nonsensical. So you have to be very, very careful with extrapolation. Now, if it's not a linear relationship, then the errors get magnified. Let's say it's actually some sort of curve like that, for instance. Well, the interpolation is really not going to be that badly off, whereas the extrapolation, where you're going off to the right, that might be off even more and a more nonsensical result. So let's take a look at an example, something that's really well studied, and there's lots of data if you want to go online and check this out, is the relationship between the size of a brain, the mass of the brain, which is usually measured in grams, and the mass of the body, which is usually measured in kilograms, with various animals. And so I've picked a couple of mammals here, a rabbit and a cat, and I found a data set online. And the rabbits that were measured had an average body weight of 2.5 kilograms and an average brain weight or brain mass of 12.1 grams. And so that's this point right here. This is the rabbit point right here. And the average body mass of the cats that they examined were 3.3 kilograms, and the average brain mass was 25.6 grams. So I've intentionally just given us 2 data points, because we're going to do the same sort of thing that we just did, which is we're going to assume it's linear, which means there is a line passing through these 2 points. And let's say that we'll draw a rough line here. So one of the things you should notice right away is that line seems to head down towards the x-axis. In other words, a body mass of around 1.8, 1.9 kilograms and a brain mass of 0. Now, that in and of itself should kind of raise some red flags to you. This is probably not a linear relationship. But nevertheless, let's say we wanted to find the mass or estimate the mass of a brain of an animal somewhere in between 2.5 kilos and 3.3 kilos. So, if we're trying to, let's say, find an animal that has a mass of 3 kilos, we could say, well, based on this relationship, it's probably going to be somewhere about 20 grams. So whatever this mystery animal is, it's going to have a body mass of about 3 kilos and a brain mass of about 20 grams. And even if this relationship is not linear, which I can tell you it's not linear, you're probably not going to be all that far off. Where we're really going to be far off is if we try to go kind of beyond these values. So for instance, what would happen if we tried to find something related to a guinea pig? So a guinea pig might have a body mass of only 1 kilogram. So this line we've got here is going to be pretty much useless for us, because if we try to find the point on the line where the body mass is 1 kilogram, you can see it's going to be below the x-axis. And so that's not going to give us a meaningful body, a brain mass. And similarly, if we pick, let's say, a dog with an average mass of 5 kilograms, we could certainly go out on the line, it'd be somewhere up here, and find a corresponding brain mass. But I wouldn't really have a lot of confidence in that. So it turns out that this is an example of a kind of a curved relationship, and the curve kind of goes along here like this, and then sharply rises. However, there's a huge amount of variation along this. Now, why would you want to have an understanding of this relationship? Well, you can use it to compare brain sizes in different animals and make an analysis as to whether or not you think that animal has an unusually large brain or an unusually small brain. And they've done that for mammals and taken a look at the brain size of humans and decided that, based on our weight, we really have a very large brain compared to other mammals that have a weight maybe slightly more than us or slightly less than us. And so that would be an example of interpolation, because we certainly have lots of mammals on either side, much smaller than we are and also much larger than we are.